Welcome back to the molpigs podcast. Joining me today are Spencer,
Hello.
Anuhia,
Hi, everyone.
and I'm Eric. Today, our guest is Megan Engel, an assistant professor at the University of Calgary, whose work focuses on harnessing the technological advances underpinning artificial intelligence to push the boundaries of physical models. She did her bachelor's and master's in astrophysics at the University of Alberta before doing her PhD at Oxford, where she worked extensively with the oxDNA model to understand the behavior of DNA structures under forces. After a postdoc with Michael Brenner at Harvard, where she dived into optimization algorithms, she returned to Alberta to start her own group at the University of Calgary, focused on non-equilibrium thermodynamics and model optimization. Megan, hi.
Hi, I'm so excited to be here. Thank you for inviting me.
So always our first question, how did you get into molecular programming? Can you say a little bit more about that experience of transitioning from astrophysics to molecular dynamics of DNA origami? And what skills transferred and where were their learning curves in that process?
Yeah, so that was an interesting and random process. So I was in astrophysics, and at the end of my bachelor's degree, I knew that it probably wasn't for me. I loved it, but I just wanted something a little bit different. So I started a master's also at the University of Alberta in biophysics, because biophysics was kind of calling out to me. And so that master's was experimental primarily, but I gravitated a little bit more to the theory. So I was doing single molecule pulling experiments on DNA hairpins and using non-equilibrium physics equalities to extract information about those hairpins. And I really enjoyed that, but I feel like I wasn't a stellar experimentalist, shall we say. So then I started my PhD at Oxford, and I actually started in a totally different field of biophysics. I was going to do quantum biology. So I was interested in the quantum nature of photosynthesis. And this was in a quantum optics lab. So this was again experimental. I feel like I wasn't getting the message that I shouldn't be doing experiments. So I started in this other lab, and for various reasons, it just didn't work out. So after 1 year, I did the very crazy thing of switching to a totally different department in physics at Oxford. And that was a really difficult decision to make because I'd invested so much time, but there was the sunk cost fallacy. And finally, I just jumped ship. And I was super lucky to, at this point, I had already used up a year of my PhD funding. And so I was keen to launch not into a totally different field, but into something where I had some basis of understanding. And so I'd already done DNA biophysics. And so Professor Ard Louis and Jonathan Doy at Oxford were working on DNA biophysics. And at this point, I sort of realized experiments probably weren't where I could shine. I should stick to theory and computation. And they were doing theory and computation. And so I thought, because I had some previous experience in DNA biophysics, they were doing DNA biophysics, this would be a great place to land. And so I ended up working with them, and they had developed the oxDNA model. They were really interested in DNA origami. And that's really how I got into it. So it was sort of a random pinball effect, me bouncing around, but I was so happy to land where I did land because I had a great experience with them. And I loved computational biophysics and kind of haven't looked back. Oh, sorry, I didn't answer all of your question though. I think you were also asking what was challenging about that transition into molecular dynamics.
Yeah, anything you want to talk about there?
Yeah, I would just say the scale of computational power required was challenging to wrap my head around, and just how long those simulations took to run. So some of the simulations I ended up running took months of GPU time. And that was really challenging, because if you kind of launch something with the wrong parameters, then in a month you look at your results and you realize you screwed up. That's very depressing and painful. So I think just the challenging learning curve was learning how to use the compute optimally, and just being very, very careful about what you're launching on those resources. And that was a whole new world for me, high performance computing. So I think that was the big learning curve.
Well, that was a great general gist of your career path, but I guess we're gonna dig deeper into investigating every part of it, starting with the paper you're most known for, which is the force-induced unraveling of DNA origami structures. So there's not really been a lot of similar work that's exploring DNA origami systems in non-equilibrium forces. So why do you think it's important to study that, or any other insight you can add to that aspect?
Yeah, so that work came kind of directly from my previous experience doing single molecule experiments in non-equilibrium settings, and also my interaction with Tim Liedel's group and Marcus Jobst, and they were doing AFM pulling on origami. So it sort of was this marriage of things that I had done previously and things that were being done on DNA origami. And the reason I think it's an interesting avenue to explore and still really important is that a lot of particularly the recent applications of DNA origami into making molecular motors, like the molecular rotary motors that Henrik Dietz's group has been working on, these things are going to have to withstand potentially quite high forces. So it's really important to understand the failure modes of those structures under non-equilibrium force. So if you're trying to recreate ATP synthase, which is the tiny rotary motor in our cells, it is whipping around, I think it's something like 10,000 nanometers a second. Like it is very far from equilibrium. And so you have to understand how those non-equilibrium torques are going to affect your origami structure if you're trying to recreate the same thing out of DNA origami. And so I think that's one really important point, is understanding the failure modes of these structures under non-equilibrium forces. But also, I think there's a lot of applications that depend upon the response of these structures to force. So there was a recent paper that was building nanosprings out of DNA origami to be a force sensor, to like kind of read out piconewton level forces. So you have to be able to precisely tune and calibrate those structures so that they behave the way you want them to under non-equilibrium forces for force sensing applications. And then there's everyone's favorite kind of application that we trot out in grant applications, but drug delivery mechanisms, right? If we're going to do cancer drug delivery, there's a lot of force-gated mechanisms that have been proposed. So there's another application where you have to understand the non-equilibrium force behavior of DNA origami structures. So I think those are kind of the important applications and that motivated why we wanted to look at it and why we thought it was important to understand the behavior under non-equilibrium force.
Something I've heard a lot from the modeling community, which again, I don't have a direct connection to, so this might be meaningless, but something I've heard a lot is that there's a lack of the raw foundational fundamental data for these models. So I'm mostly familiar with thermodynamic equilibrium models, and a lot of them still use the data from Santa Lucia, and that's it. That's all we got. What is your take on the need for the base level experimental raw data, and how can we encourage labs to provide more raw data for these models?
That's such a great question. And I've been thinking about this a lot recently in the context of a potential collaboration with Rebecca Taylor at Carnegie Mellon, who does a lot of work on peptide nucleic acids, which are really exciting systems. And there's a total dearth of experimental thermodynamic characterization data on these systems. And so if you want to train a model, you need something like what the Matthews group did. You just need a ton of optical melting experiments. And I think you've kind of highlighted something important, Spencer. It can be difficult to convince an experimental group to spend a year just collecting really detailed melting measurements for a bunch of different sequences. But it is so important. So I don't know if I have an answer as to how we convince experimental labs to do this. I think Rebecca has seemed open to investing a bunch of time into characterizing the PNA systems and really getting some good melting data on them. So I'm excited about that. I think maybe making it clearer how important it is to have a wealth of that thermodynamic data to have an accurate model. You cannot have an accurate model without it. Maybe highlighting that a little bit more and just having conversations with experimental groups who have those capabilities and sort of highlighting, hey, if we had a model that was accurate, you could do X, Y, and Z. To get that model, we need you to do hundreds of hours of optical melting experiments. Please do them for us. I don't know, but I'm open to that. I'd love to have those conversations more, because you're right that the models are only as accurate as the data that we can train them on. And yes, we're all still using the Santa Lucia stuff, which we love. Thank you, Santa Lucia. But for these new and emerging systems, like non-traditional types of nucleic acids, we're going to need more data. So I haven't really answered your question, but it is crucial. We need to do more. And I want to convince experimentalists to do it. So if you have any ideas, I'm all ears.
quick follow-up on the Santa Lucia model. I don't know if you know the answer to this, but there's been a number of kind of higher throughput DNA melting experiments that have done or on more diverse sequences, but I've never really seen them integrated into tools. Do you know why that is and why we just keep using Santa Lucia?
Yeah, that's a good question. Actually, I did see, I should be more up to date on the literature here for this recording. But I did see a paper recently, I want to say it was from 2022, that was trying to fit. It was trying to do something. It was trying to fit melting temperature data directly. I don't know if they were doing some sort of machine learning model, but they were trying to bypass the nearest neighbor model, and they were just trying to improve by fitting melting temperatures directly. I can't remember. I have to look into it again. I can send it to you if you're interested. But so I think people are doing it, but you're right that it's not for some reason taken off. I don't know the answer to that. I think probably because of inertia. We understand the nearest neighbor model. We like it. It's been successful. Why poke the bear is maybe what's happening. And I think there's this effect in science where you kind of build on the scaffold that's been erected. And so people have already used this model to great success. And so you want to kind of build on that and not tinker with the underlying assumptions. And I think this leads into a problem that I think exists in the molecular modeling community that I want to help address. But there's sort of people just kind of assume the things that have always been assumed and do it the way it's always been done. And that is a real problem for the accuracy of molecular models and the reproducibility of molecular models. And in particular, the ability to improve on those models quickly and robustly. That is lacking hugely in the biomolecular modeling community for reasons like what you've just identified. Like maybe there is better experimental data, but there's no coherent way of integrating it quickly into the models. Like let's say we wanted to reparameterize oxDNA because we have access to better melting data. And there is recent, like last year or this year, actually, there was a paper on salt-dependent DNA melting curves that I would love to introduce into the oxDNA thermodynamic fitting. There's no clear way or like roadmap for doing that easily, or there hasn't been. This is kind of what I'm trying to do with my current work, is provide a roadmap for when new experiments become available, quickly integrating them into the existing scaffold. Yeah, I don't know if that answers your question. I wandered there. I really meandered there.
That actually goes into my follow-up question, which you're kind of hinting at this like traditional gap that exists between experimentalists and modeling experts, where like the modeling people are like, I wish we had more data, and the experimentalists are like, I wish these models made sense to me. Like there's a little bit of a barrier in understanding what the modeling is, right? And you're in a really special position in terms of your experience, where even though you said, oh, not stellar experimentalists, like you've designed experiments and they're hard, but and you've also worked with a lot of models. So like in your experience, like how has one affected the other? But in like a more specific way, I'm more of an experimentalist. So how do I keep in mind my data is actually usable by future models that maybe are not being made immediately, but is going to be made in 5 years, right? And if I was developing models, how do I make these like relevant and accessible to the current experimentalists? Like generally, how do we bridge the gap, right?
Yeah, that's such a great question. It's so important. I think it's just so important. It sounds really cliche and like a silly answer, but I think talking to each other is the main thing to do. Just sit down and have conversations and visit. So one of my favorite experiences during my PhD was actually visiting the labs that were making the DNA origami structures and seeing how it was done and watching them do the experiments, watching them mix the origami up in a little tiny test tube. That really has stuck with me because I had no idea what it actually looked like to collect those AFM experiments and to create the DNA origami. So I think for theorists and modelers, visit the labs of your collaborators. Send your students to visit those labs and watch the experiments being done. Send them to hang out with the experimental groups and like go to a concert together and just become colleagues and peers, and those types of conversations will naturally happen, and then the modelers will naturally develop an appreciation for how difficult those experiments are, what the limitations of those experiments are, And then likewise, the experimentalists will develop more of an appreciation for where the modeling can be useful, where it can be supplementary to the work that's being done. So I think, yeah, for the modelers, we need to have an idea of what are the questions that the experiments can't currently answer. What are those scales, time scales and length scales, where it would be useful to have a molecular simulation. I always think about molecular simulations as a different type of microscope. It's a microscope that lets you access something that the microscopes you have can't see. And so what are those scales that are interesting? What are those missing pieces that the experimentalists are really wondering about? Where can you kind of plug in the model and have some synergy there? And then also the modelers, I feel like if you're a theorist and you're not talking to experimentalists frequently and collaborating with them frequently, this is a personal bias, but I feel really strongly that you should be, because otherwise you're untethered and you just float up into the sky. And yeah, maybe you're doing some really beautiful theoretical work, but if there's no clear path for integrating that into experiment and ultimately into applications, I think it's of limited utility. I think knowledge is beautiful for knowledge's sake. We can all be idealists and the beauty of the scientific endeavor. Okay, maths is beautiful. But we have to build those bridges so that those effects can trickle down into actually improving people's lives. And one important first step is for the modelers and the theorists to talk to the experimentalists and be in those labs and see what is possible, what is not possible, where can I be useful as a theorist. I don't know if that answers your question, but yeah, just talk to each other and also make friends with, there's a few unicorns. Eric, you're one of these people who do both well. And Tom Aldridge is another one of these people. And Peter Sulk is another one of these people who is doing both. And so talking to people like that, they have a really interesting and a unique perspective. So I enjoy being friends with the unicorns who can do both.
Yeah, and this really echoes something that was said during some of these molecular programming flight planning meetings that we released as podcast a couple of weeks ago, where something that people really said was we want to get the experimentalists and the theory people together and have them exchange students so that everybody understands both sides. So it's good to hear that yet again, that this is a thing that people in the community think is important.
Totally. Yes. I have my first graduate student starting this fall. But a plan, and I have a training plan for they're called in Canada, they're called highly qualified personnel that you're training on all the grant applications. So I have a training plan, and part of that is sending my students to the labs of collaborators for a couple weeks to just hang out there.
Let's get even more specific with this. So your current work revolves around this technique called automatic differentiation. And what you're planning to do is to use that to kind of integrate these experimental systems into models. Can you explain what automatic differentiation is and how it works and why it's interesting for this use case?
Yes, sure. Okay, so automatic differentiation, something people say a lot is the easiest way to explain what it is starting with what it is not. So it's a way of computing gradients or derivatives, which is just, an idea of how does one variable change as you change a different variable. And there's a technique called finite difference methods that people will use to compute gradients. So if you have some discrete experimental data and you want to understand how one variable changes with respect to another, you kind of just take discrete slopes between points, and that's finite difference methods. And there's a lot of cumulative errors that come along with those methods. There's also symbolic differentiation, which software like Mathematica will do for you, where it will come up with a symbolic expression for what the derivative is. Automatic differentiation is neither of those things. It's kind of in the middle. So it's an exact method, correct up to floating point errors in computers, for computing the gradients of data. And it's what underpins modern machine learning. So when you train neural networks or deep neural networks, you have to be able to compute. It's a process called backpropagation. You basically have to be able to compute how does your loss function, which you want to minimize, how does that vary with your input parameters? And by performing some sort of stochastic gradient descent on a loss landscape, you take steps towards the Bayesians of minimum loss on your loss landscape. And so you can train your neural network. You vary the parameters by computing the gradient of your loss with respect to those parameters and taking steps on your landscape in the direction of that gradient. Or the negative direction of that gradient to find the minima on the landscape. So this is how you train neural networks. And so it's a really efficient method. It's kind of like I like to think of it as a chain rule. Basically, in the computer, all computations are represented. You can think of like computational graphs, and each node on the graph is a primitive operation. So like the simplest possible operation you can think of. Any complex simulation or neural network is broken into the minimum steps of multiplication, addition, subtraction, simple trigonometric functions. So I could think of like sine x, x1 times sine x2, like each of those simple primitive operations is another node on a graph. And you can think of like a tree-like structure of all these primitive operations. And the thing is, you know analytically what the derivative of a primitive operation is. I know that the derivative of sine is cos. And I know that, exactly. I know that the exact derivative of that step. So if I can break my whole computation into all these primitive steps, on each edge between nodes, I know the partial derivative. It's a simple derivative. Then I can compute my ultimate derivative using the chain rule by multiplying the derivatives of each of these edges together. And I can store that net derivative as a multiplication of all these primitive derivatives. So that's what modern machine learning libraries are doing to train neural networks. They need the derivative. They need to perform backpropagation to get this net derivative so that they can minimize the loss and make ChatGPT talk to you properly. And so automatic differentiation is how they do it. And the reason that I think it's really powerful in the physical sciences is because private companies, where there's a lot of money to be made, have invested huge amounts of dollars in optimizing the hardware and software that performs automatic differentiation, because ChatGPT is making a lot of money. And so they have a vested interest in making automatic differentiation libraries work really well. And so I think there's a lot of potential in harnessing things like TensorFlow and PyTorch, and JAX is the library I use, these machine learning libraries that can perform automatic differentiation really efficiently on GPUs. They're automatically hardware accelerated to use the latest GPUs. So you don't have to worry about reprogramming. You don't have to sit down like poor Flavio and Lorenzo did and rewrite everything in CUDA, because those things automatically are hardware accelerated. And now we can use those tools on problems of interest in the physical sciences. So we can, and there's optimization problems. That's all that training a neural network is. It's an optimization problem. And there's optimization problems everywhere in the physical sciences, right? And so we can use that hardware and software now to solve optimization problems that we are interested in. Like, how do we build the best coarse-grained DNA model? What's the optimum parameters for oxRNA, right? So I think there's a lot of potential there in harnessing AutoDiff and libraries like JAX to solve those problems for us.
I really want to see the new DNA model, but what else are you planning to apply it to? And I looked at your lab website. It seems like you have like a big visions for more than just DNA and RNA.
Yeah, I'm just so excited by the potential of this. So I think one area where I'm really interested in applying this technology for optimizing or optimization problems is looking at naturally evolved systems, and then the flip side, trying to design synthetic analogs of those systems. So I'll give a concrete example. The ATP synthase rotor, which I mentioned earlier, is this small rotary motor that sits in your membranes of your cells and harnesses a proton gradient to create ATP, which is kind of like, you can think of it as an energy currency in your cells. Everything your cells do requires energy. And this is like the money that they use to perform all those functions that require energy. So how do you actually get that money? Well, ATP synthase makes it for you, harnessing a proton gradient to do this. And the efficiency with which it transduces energy from this proton gradient to the chemical bonds of ATP is nearly 100%, which is crazy because it's a very noisy environment in your cells. It's far from equilibrium. So trying to understand, how did evolution optimize that system? And there's other examples of molecular motors that are absolutely amazing. How did evolution harness the laws of non-equilibrium physics to create this optimal system? And what are the objectives it was optimized with respect to? That's a question that I'm really interested in. And I think by using something like automatic differentiation on a model of ATP synthase, we can start to understand the physics behind, if you want to design a rotary motor to optimally transduce free energy, what torque profile should you use? That's like a fundamental physics question. We can use AutoDiff to answer. We can use AutoDiff on these Brownian simulations of rotary motors to find, optimal protocols for operation. Then we can compare it to what we see the natural motors doing. And then we can answer questions of biophysical interest because we can say, oh, is the naturally evolved protocol the optimal one for free energy transduction? Or is there something else in the objective function that evolution was operating under? Is it also trying to optimize robustness to noise? Is there some multidimensional loss function that was at work here? And then we can use the insights we get to design artificial rotary motors, because we can say, okay, here's the torque protocol you should have if you want to transduce energy 100% efficiently. So those types of optimization questions that sit at the borderline between de novo nanotechnology and biology, I'm really interested in applying AutoDiff in that space.
The JAX-DNA tool that you've developed is a really powerful way to apply auto-differentiation specifically to things that resemble the oxDNA and oxRNA models. And reparameterizing those models is something that people have been really long scared to touch. Like every time I talk to Peter about it'd be really great if the models did X, Y, or Z, he'd always, tell some horror story about how him or Tom or Ben spent so long twiddling numbers and then wasting their life and getting gray hairs waiting for the correct model parameters to fall out. What's your vision for how this will change the field when we have an easier way to get new models out of oxDNA?
I think this is a really important question. And our vision is to make it easier to do what you've described the architects of the model were kind of scared to do, because it is very, very difficult. So a really great microcosm that illustrates my vision is a recent paper that came up with a model, MAD DNA, to accurately represent the twist-stretch coupling of DNA. Because in the oxDNA model and another leading coarse-grained model, 3SPNC, 3SPN2C, I don't know what they're on now, but it's also a really great coarse-grained model. The twist-stretch coupling has the wrong sign. So it's meant to be negative, but it's positive in oxDNA. And so what would be really great is to just be able to take all of the work that's gone into the oxDNA model and just tweak it a little bit, tweak the parameters a little bit to represent the twist-stretch coupling properly. That is so difficult to do that instead these other authors, Asenza and Perez, went through this Herculean effort to create a new model that accurately represents G, but probably misses a lot of the great things that oxDNA was able to capture. So our vision is when you have a problem like that, where your coarse-grained model that you have is deficient in some way, so we can think about non-canonical base pairing, which we all want to introduce into oxDNA. Instead of kind of developing a new model from scratch, what JAX-DNA allows you to do is to start with the parameterization and the force functions of oxDNA, all the things we love about oxDNA, and just tweak it a little bit to add a new loss function there, which will constrain those parameters to now accurately represent what you care about. Or with non-canonical base pairing in particular, I suspect we're going to have to add some new energy terms to the force function. So instead of, being very petrified to do this, because it is very difficult, we can start with the force functions that we already have for oxDNA and add one new term, and then reparameterize everything according to what should be a very transparent and robust and repeatable procedure, which is the nice thing that these machine learning libraries allow you to do. You can kind of record, okay, well, here's the optimization protocol I used, here's the loss function I used, here are the weights, because you might want to be able to weight things a little bit differently depending on what you care about. If you really only care about macroscopic, I shouldn't say macroscopic, but you kind of large scale DNA origami structures and the origami behavior, maybe you care more that the helices twist the right way than you care about very detailed kind of base pair structure. So then you can weight certain objective functions more heavily and kind of come up with a tweaked version of the oxDNA model, oxDNA tweak, for your particular use case. And that becomes something that hopefully in the vision, an experimental group can do, an experimental group in collaboration, with computational people can do feasibly, rather than it taking 3 years and an entire postdoc to add one small feature to the model. Now it becomes something that is kind of routine. That's sort of the vision. And I should add, we were using JAX-DNA as the working title, but I think we have to come up with something else like JAX Biomol, because we're in the process of applying the same framework to lipids and proteins, starting from the Martini coarse-grained model. So it really is a general framework, it's kind of molecule agnostic. You can use it on whatever biomolecule you want. And the idea is to bring the paradigm of machine learning models where they're trained rapidly and they're iterated upon rapidly by the community. The community will say, okay, well, I started with your model and I added one graph neural network for this effect. And now here's my new model. And you can kind of, in a principled way, build on the scaffold that the modeling community has erected. So that's our vision for lipids, proteins, and DNA, RNA, and peptide nucleic acid, and any kind of biomolecule you're interested in modeling.
So one last nitty-gritty question on this before we move on to other things. So your PhD advisor, Art Louie, always likes to talk about how there's no free lunch in coarse-grained modeling. And every time you like optimize toward one thing, you lose something else. Do you guys have a good way to measure like what gets lost as you re-optimize the model and kind of what it's getting worse at as it gets better at the new experimental data that you're adding into it?
Yeah, that's a really great question. Yeah, Ard wrote a great paper on this that I cited in my thesis. And yeah, there's no free lunch with coarse-grained modeling. It's true. You can't be perfect at everything. But I think this is where this framework is really nice because so one feature I really like about using this autodiff to optimize the model is you can see which parameters of your force field have the largest gradients for a given objective. So let's say I'm only going to optimize for melting temperatures. Then I can retrain the model and I can see which parameters have the largest gradients. Is it the hydrogen bonding parameters? Is it the stacking? Is it the coax? You can see what knobs you need to turn to get a given result. And so there's some physical insights you can get there and you can leverage. And then what you can also do is you can look at what I can imagine doing to answer the question of what gets worse is you can kind of set up all of the different classes of behavior that a modeler and experimentalist cares about. So structural, mechanical, thermodynamic, kinetic. So this is the other thing, by the way, total tangent, but I'm really excited about the possibility of incorporating kinetic data into the fits. That has not been done. So you can kind of list all of the loss functions that you would ever care about. And you can specify weights, which ones are you most interested in? And you can, within each of these classes, there's subclasses. So there's like the stretch modulus, there's the torsion modulus, there's for the mechanical data. And the thermodynamic data, there's, the melting curves and the widths of the melting curves. So there's all these different loss functions you can think about listing and computing. And in the JAX-DNA framework, we have all these for you. So you can kind of import, okay, melting temperature, okay, stretch modulus loss function. You can imagine training the model to really capture the twist stretch coupling, but you care a lot less about the maintaining the thermodynamics. So you can either dispense with that loss function entirely, not even train to thermodynamic data at all, but you could still monitor what that loss would have been, right? Like you can still compute how good am I doing at the melting temperatures with this new model. And you can keep an eye on that. And if it's deviating way too much, then maybe you think about incorporating that thermodynamic loss with a smaller weight. Like maybe it's 10 times smaller than my twist stretch coupling weight. So you can prevent it from deviating too large. And you can decide what compromise you're okay with. How bad are you okay with doing? And of course, as Ard pointed out, it is a compromise. But at least now I'm going to be able to put numbers on all of these loss functions. And I'm going to have a really clear idea of what I'm sacrificing when I turn different knobs.
Shifting gears completely from research to your career and your experience now as an assistant professor, I want to pull it all the way back first before we get into what you're doing right now. Can you tell us about how you prepared for getting your new position? What was your process and experience getting where you are now?
That's a great question. So I think one thing I did was I applied before I was ready to apply, and that was helpful. So I had, I think 2 years on the market where I think like right out of my PhD, I started applying because there was a position at Oxford in biophysics, and I loved Oxford, like just on a personal level. It was just the most beautiful place. And we may get into this later, but I'm an enormous Tolkien nerd. Tolkien lived there. So, my dream was like, can I live here forever somehow? And so they were recruiting, and I think I just graduated from my PhD, and I was like, what the heck? I'm going to apply. And of course I didn't get it, but it was a really informative process. So I think just the act of trying to coalesce a research program is super helpful. So in science, I think in terms of getting a faculty position, and this varies from institution to institution, because some places, in my opinion, erroneously put a lot of weight on number of publications. And some places are just, particularly in physics departments, I find they're just interested in how many papers you've published. And so if if you don't meet their bar, there's not a lot you can do about it. But I think that what's, personally what I feel is most important as a scientist is to be able to articulate a vision of a research program and differentiate yourself from other scholars in the field through that vision. So how do your skills serve the vision of the type of research you're going to do? I think you can publish a ton of first author Nature papers, but if you don't have a cohesive vision of how you will contribute to the body of scientific knowledge and the creativity that underpins that plan, you're not going to be able to be, I think, successful as a scientist. And so for the faculty interview process, applying before I was ready was really helpful, because you have to write that research statement. And then if you apply the next year or the next cycle, you have to rewrite it and tweak it. And so the first research statement that I applied with was very different from the final one I applied with, but it was just helpful even as I was going through my postdoc to be iterating on that vision. What is my vision of what questions are interesting, and how will I uniquely contribute to those questions with the skills that I've amassed?
You recently started your own lab at the University of Calgary. How has your experience been starting your own group? What is your vision for your group? And do you have any other insights from this process?
Yeah, that's a great question. I think I just want to preface it by saying that giving insights and advice as a faculty member to people who are at the PhD or the postdoc stage, it's always a little bit fraught, because I think the process is fundamentally so random. And this is something I want to really emphasize for people who are getting their PhD and who are in the postdoc stage, kind of looking ahead to maybe that faculty position, the elusive faculty position. It is really a matter of luck in such large part. And I think often of a Jean-Luc Picard quote from Star Trek: The Next Generation, which is that it is possible to make no mistakes and still lose. And it's really not a reflection on your worth certainly not on your worth as a person. And it's not even a reflection on your worth as a scientist if you are struggling to get that faculty position, because it's influenced by so many factors beyond your control. There's what the current government funding priorities are. That really strongly influences what fields departments can hire in. So you can be a stellar scientist just in slightly the wrong area, and have trouble finding success. So I feel very fortunate, and I also feel kind of ill-positioned to advise, because everyone's path is so unique. I remember getting advice from one of my supervisors, and he said, you can't go to Europe for your PhD if you want to have a job in North America. You have to go to the United States and that's simply because that's what he had done. But everyone's path is so different that sort of looking to a faculty member and seeing, okay, how did you do it? What was the exact roadmap? It's of somewhat limited utility, because it depends on so much stochasticity in my own process. But I feel very, very fortunate, because I got a faculty position. It happened to open up in my field in a city that's quite close to where I grew up. So I really feel like I won the lottery in that respect. It has been a really amazing experience to kind of come back to. Alberta is the province that my university is in, and it's also where I grew up. So I've been able to be close to family and start this position, which has been amazing. And also being able to, I think one thing I've enjoyed a lot about setting up my own group is the moment that I decided that I wanted to be a professor was in a second year electrodynamics course, because my professor was teaching so poorly, and I could see the light bulbs turning off in people's heads and their eyes glazing over right before my eyes. I could see people draining out of a leaky pipeline from physics. And I just thought at that moment, I was like, I could teach this better than you today. So and sadly, that was not a unique experience in my education. And so I just thought, I really want to be in front of people in a university setting teaching something physics related, because I think that I can animate it more than this guy. And that was the moment that led me on this path to the faculty position. And so now finally getting to be in that position, I've found really gratifying, because I've been able to do things that hadn't been done for me. So I've set up like a lab expectations document where I explain very clearly, this is my mentoring style. If this doesn't work for you, it has to be a fit for both of our sakes. So just, here's in advance upfront what I'm going to expect of you, what you can expect from me. That would have been so helpful for me to have along the way. Although I have been really fortunate to have amazing mentors. I've had a lot of experience with, particularly with teaching professors that, anyway. So that's been really great. And I've been able to put a focus on, seeing the whole person, seeing people as a whole person who should take breaks and should take vacation and should have a balanced life. And that was something that was really missing for me in academia as well. And then I've been able to sort of set the parameters regarding how important is it for us to publish or perish? I get to have a little bit more control over that. I'm not tenured, so I may, you should maybe ask me if I get tenure before you take any of this to heart, because I may not. But I'm basically forging a different path, I feel like, in academia, and I'm going to do things differently. Hopefully I still get tenure, but there's a lot of things I think that need to change. The publish or perish mentality needs to go. It is not good. It does not incentivize risky or meticulous science. I'm done with it. There's also things like, I remember applying for a faculty job. I'm really meandering now. Sorry, I'm going really off topic. But when I was applying for the faculty job, I got a lot of feedback on my application package, which I would also recommend, and specifically get feedback from academics in different countries because the systems are so different. So if you're applying in the US, get feedback from someone in the US. If you're applying in Canada, et cetera, et cetera. So I was sent my package to a mentor of mine, and I had my maternity leaves right on the front. Like, here's my leaves. And at that point, I'd taken 2 maternity leaves. I've now taken 3. But I remember getting the advice back, it's laudable that you're trying to do this, but you should take this off the front page because you're not going to get hired anywhere. We're just not at that stage yet. And I didn't take it off because I don't want to get hired in a department that would make that a prerequisite for hiring me. So that really helped to just kind of be honest about who I am and what's important and how I'm not going to. And there was another faculty process where I got asked how many papers a year, or an interview, sorry, where I got asked how many papers a year I would publish. And I just thought, like, the fact you're asking this question makes me not want to work in your department because your focus is not on what cool science I'm going to do, which might take multiple years to, manifest into a publication if it's good science. It's on what are my numbers and my metrics going to be? That's just like so misguided. So, all of this to answer your in a very long-winded way to say, starting my own group has been really gratifying because I can kind of break the cycle in a lot of ways.
I think you're speaking to a lot of the thoughts and feelings that I've heard just coming from this younger new generation of professors and academics in general. So hopefully we're going to make a shift in things. Hopefully, fingers crossed. Going a little bit back, how has been the jump between all of these different countries, processes, and systems and 2 entirely different continents? Has that been particularly complicated, or has it been pretty smooth?
In a personal sense or in an academic sense?
Either. I mean, luckily, it sounds like you've moved back to family and a home, but regardless.
Yeah, I think it's been, valuable is the first word that comes to mind. It's been valuable and enriching to be in such different contexts. I just learned so much from being exposed to different ways of doing things. So that's been really valuable. I mean, I shouldn't give advice on what you should do in your career, because as I've said previously, it's really person dependent and situation dependent. But having the experience of working both in Europe, and I was in the UK and in North America, was really valuable. I really enjoyed that, both in a personal sense. I think it made me a better person, and in a professional sense, because you kind of learn what's possible and then you can pick what you like. So for example, I found the pace of research was very different in Europe compared to the US. So I was at Harvard, and the Ivy League schools, I think in particular, can be a grind. People are there to grind at the grindstone. And Europe was very different. People were, if it was a sunny day, going off for a picnic. And so I personally really preferred the picnic style situation, because I feel like you can have really great ideas if you're walking to a picnic. That scientific ideas can happen there if you're relaxed and happy. But just seeing both sides and really kind of getting an appreciation for how the system works, how the funding system works, in different places, how it's influenced by the governmental priorities in different ways, depending on what country you're in. It's been really interesting and really valuable, and has also allowed me a little bit more freedom to kind of choose what works for me. Because I know that there are, academics on the European model who are not working 12-hour days, and they're still really great scientists, and they're contributing to the scientific body of knowledge. So it allows me to see that actually that's not necessary. Whereas if I was always in a lab where there was this presenteeism and you have to be there 12 hours and, your hours are being counted, I might not know that it's possible to be successful doing it differently. So that was helpful.
So you've talked a little bit about starting your own group and like your vision for it and how you're trying to break the cycle and foster a good working environment and everything. But how do you recruit for your lab? Like, what kinds of talents and skills are you looking for? How do you find a good match for your style, I guess?
That's a great question. That's something I'm still working out because I've just accepted my first grad student starting in the fall. So I've so far been supervising undergrad. So I've supervised about 9 undergraduate projects. And so far I've been advertising on mailing lists and websites and at conferences. And whenever I give a talk, I plug that I'm recruiting. And the main things I'm looking for, one thing that comes to mind that's like, I don't know, maybe kind of silly or minor is if the email that reaches out to me is very clearly written with ChatGPT, I usually don't respond because I don't love that. I mean, AI is very useful in a lot of ways, but I think it can't really replace genuine interest in human connection. So that's one like very simple thing. I think in terms of like skill set, I'm really interested in people who are curiosity driven, who are genuinely interested in these questions. And also humility is a big one. I've had a few interviews with people who just were not a match, where there was just like a little bit of condescension or a little bit of, sense of superiority, a little bit of pretense. I don't have time for that. I'm interested in like genuine people who are aware of their own limitations and who are humble, who are approaching science with humility. Because if you're not approaching science with humility, you can't do it well. I really believe that. So, humility, genuine curiosity, and I think a good sense of work-life balance is important, at least for me, because I strive to have a work-life balance. So if someone really wants to just grind at that grindstone, it's not going to be a good fit to be in my lab because I'm not really available to answer emails on weekends and evenings, and I'm just not going to get back to you. So that would be a very frustrating experience for a student that was wanting to work like 12 hours a day. So I think that's also what I'm looking for, like a good fit in terms of like life priorities and working style.
I think that's a really healthy and wonderful way to think about who you're accepting into your lab. I have one quick question is, I feel like, especially as a new graduate student, there is a lot of pressure to lie about work-life balance opinions and beliefs. How do you kind of feel out how much of their I want to work 12 hours is the truth and how much of that is them just wanting to impress you?
Right. That's such a good question. That is such a good question.
I guess there's an argument to be made that if they're already lying to you, maybe that's a bad sign, but
it's maybe a bad sign. Yeah, if they're already lying, maybe a bad sign. But I do have sympathy for people feeling pressure to present a certain way. Like in my department, I think University of Calgary is like pretty good, and I've really enjoyed working here, and I think it's pretty good in terms of work-life balance. But I will still hear faculty members in the elevator kind of saying things like, "Oh, I worked all weekend again," or "I forget what it's like to go to concerts," or just sort of almost bragging about how much they're working and like, "Oh, I put in another 70-hour week," and I feel kind of bad for them because I feel like you must feel under some pressure to say that. But I think there's some pretty good scientific evidence, and at least anecdotal evidence, that no one is being productive for 70 hours a week. No one is being productive for 8 hours a day. Like if you're trying to ideate and do really high level creative work, you cannot do that for 8 hours a day. You can't really do it for 6 hours a day. Maybe you have like 15 minutes where you have a brilliant idea and then you kind of coast off of that for the next 2 years. Like science is really fits and spurts. And so I would be pretty suspicious if anyone was like, yeah, you put in 12 hours a day. Like, I know you're not being efficient for that amount of time, and it's not healthy. And personally, I have way better ideas if I feel relaxed. Like my best ideas I've had like in the shower or on a walk. Yeah, so I guess, but your question is, how do you suss it out? I don't know. I think you just kind of get a sense. Like you just kind of get a sense if someone's on the same page. And even if they're not, I feel like maybe I can show them they don't have to lie about it, and then they can feel some relief. They don't have to pretend to do that. Because I'm just being honest about it. Like I don't know if I don't even know if I should reveal on this podcast, because I might get some shade from the community or not get tenure. But like, if I'm honest about the number of hours a week that I actually do useful work, it's never more than 40. It hasn't been more than 40 since I graduated since I became pregnant with my daughter. I've never worked more than 40 hours in a week.
That's definitely in keeping with the current efficiency research, I would say.
Yeah, well, you just have to be efficient. And you really realize when you become a parent how much time at work is not working. It's like socializing, or it's like getting a snack or a coffee. Like there's just, you become really efficient. You just get in there, get what you need to get done, and get out of there. And it doesn't take 8 hours.
All right. Our very last question. Where do you see the field in 10 years, and what do you hope to have accomplished?
I'm really excited about the work that's being done in DNA origami-based molecular motors. So Henrik Dietz is doing this stuff with making artificial ATP synthases. I'm super excited by that. And I think that is just going to explode. And also work kind of complexing DNA origami with protein and with lipids, and making these like multi-biomolecular structures. I think that's really going to explode. And I'm really excited to be part of that, like the de novo design of molecular motors. And I hope in 10 years to have provided a tool that is being used to create the most accurate coarse-grained models to date that are being used to design those technologies.
Well, we want to ask you about your last two oxDNA dev conferences, and they've kind of been your J.R.R. Tolkien tour around Oxford. Can we hear your favorite Tolkien life or Middle Earth fun fact?
Yeah, I'm a huge Tolkien fan. So at the oxDNA development conferences, I do give like a J.R.R. Tolkien around Oxford. So come for the DNA, but stay for the Tolkien. I like have so many favorite Tolkien facts, but I might just have to leave it at, I named two of my children after Tolkien characters. My daughter's name is Laurelin, and my son's middle name is Telperion. And those are the two trees that provide they basically provide the sun and the moon eventually in the Silmarillion. So maybe leave it at that.
That's so cool. That's pretty cool, actually. So that was a very fun question to end on. Thank you so much for joining us, Megan. Stay tuned to our newsletter or Slack for details on our upcoming podcasts and reading groups. Thank you all for listening.